Hello and welcome to 7.6 Circular Reasoning. We've got a bit of a couple of puzzles here today, and the second one is going to be, on this next page, is going to be a bit of a bear, so go ahead and strap in and hold on for the ride. But we'll start with this first one. So it says the following problems will draw on your knowledge of similarity, circle relationships, and trigonometry. This is also, when they say similarity, they mean triangle similarity, triangle congruence, and all sorts of stuff, okay? So, the following diagram, the radius of circle D is 5 centimeters, and F is the midpoint of segment AE. Segments GE and GA are tangent to circle D, and the measures of arc EB and arc BC are in the diagram. Find the measures of all other unmarked angles, arcs, and segments, okay? So, we've got a lot tasked before us. The first thing you can do is just go ahead and mark all the radii as congruent, right? That's a nice, easy first step so that we feel like our first step is accomplished. So I'm going to go ahead and say segment BD, segment DA are equal to 5 centimeters. So, and I'm just going to make it a little simpler too. Segment BD is equal to segment DA, which is equal to 5 centimeters, right? So they're just all equal to 5 centimeters. I know that because they're radii. So now let's look at some angle measures here, okay? So we know that angle EDB, that's a central angle, right? Because its vertex is on the center of the circle. So I know that it will be equal to the arc that it intercepts. So angle EDB is equal to, or the measure of angle EDB is what I should say, is equal to 40 degrees because that's the measure of the arc which it intercepts. Then I also know that an inscribed angle here is equal to half the measure of the arc it intercepts. So I can say the measure of angle BAC is equal to 30 degrees because it's half that arc measure. I'm going to do the same thing actually with EAB, right? Because we see that it intercepts this arc EB up here. And so the measure of angle EAB is equal to half of 40, which is 20 degrees, okay? So as I go to, I'm going to just put little check marks in things that I've gotten, just so I know and I'm keeping track of everything, right? Now, let's see. How could we figure out these other arcs and whatnot? Well, let's look at arc AC right over here. So I know that BA is a diameter, which means it intercepts half of the circle, and I know that half of a circle's degree measure is 180. So now if I take out the 60 that we know with arc BC from that 180, I can figure out that arc AC that I'm looking for is equal to 120 degrees. So I can say the measure of arc AC is equal to 120 degrees. Cool. So that one's all squared away. Now I have just part of the arc left, right? I just have EA, arc EA. Now, I know that arc EA is the only thing that's left, so I can subtract all other arc measures from 360, and that should give me the measure of arc EA. So the measure of arc EA is equal to 360 minus 60 minus 120, so that puts us at 180 minus 40, and that is 140 degrees. So the measure of arc EA is 140 degrees. So we've got that squared away now. Okay, let's also look at just the measure of segment BA real quick, just for good measure. Let's put that in there. We know that it's a diameter, and diameters are twice the length of the radius. So the measure of, or the distance from B to A is 10 centimeters, twice the radius. Okay, now we need to do some other stuff real quick. Well, I know that I have a lot of right angles in here, don't I? I can see that this is a right angle. Now, why do I know that that's a right angle? Well, I can see that angle BEA, it intercepts a semicircle. It intercepts half of a circle, which means that the whole arc BCA is equal to 180 degrees. And I know that angle BEA is an inscribed angle, meaning it's half the arc measure that it intercepts. So I know that that is 90 degrees right there. Okay? I could say the same thing about BCA for the exact same reason. It intercepts the semicircle. That's exactly half of the circle with the diameter. So I know that it is a right angle because it's half of 180 degrees. Now, I have this angle measure right here also, which is 30. And that must mean that this angle measure over here is 60 degrees. Awesome. Okay. So now I'm at a point where I can use some trig too, because I know that the diameter is 10 centimeters. So I can use that in a moment as well. So let's go ahead and do that. Let's find the lengths of segments BC and CA using some trig. Well, I'm just going to go ahead and use this one right here. So I need to find both CA, which I'm going to call X, and BC, which I'm going to call Y for right now. So I need to set up some trig functions. I know that the hypotenuse of that right triangle is 10 centimeters. Okay, and so I'm going to use cosine first to find X because it's adjacent over hypotenuse. So cosine of 30 is equal to the adjacent side over the hypotenuse. Okay, so when I rearrange that, it gives me X is equal to 10 times the cosine of 30. Okay, and then when I have when I need the opposite side, I'm going to use sine, so, right, because of so katoa. So I'll use sine of 30 degrees is equal to y over 10. So then when I rearrange that, I get y is equal to 10 times sine of 30. So I'm going to go ahead and plug that into a calculator really quickly. So sine of 30 is equal to 0.5 times 10. So I know that sine of 30 times 10 is equal to 5. Okay? So that's 5 centimeters. Awesome. Wow, that's interesting. It's the same as the radius, actually. Then I'm going to do the same thing with cosine. So cosine of 30 cosine times 10, and that is equal to 8.6. Or 8.7, let's say 8.7. So 8.7 centimeters. A little bit less pretty, but it works out just fine. Okay, so now we've gotten those taken care of. Done with those. So now let's tackle some other ones. Well, I know that this is a 20-degree angle right here. Okay, so let's look at maybe this triangle FAD really quick. I can see this looks like a right angle to me, but I'm not totally sure yet that it is, right? So I'm going to need to do a little bit more sleuthing before I can know for certain that that is a right angle. Let's see. Well, one thing that I do know for certain is that F is the midpoint of EA, which means that this, and here, let me switch colors here so we can keep track of exactly where we're at. So this AF is congruent to EF. Okay, then I also know that FD, well, that's itself, so it's going to be congruent to itself because it's reflexive, the reflexive property of equality. And then I see that DE and DA are both radii, so they're congruent to one another as well. So I have some triangle congruence right here, which means that over here, that angle is also 20 degrees, okay? So I have 20 degrees and 20 degrees. I know that these sides are congruent, so once I find EF, I'll also have FA, and similar to that, once I have FD, I have FD, because it's the reflexive angle, it's itself. So, let's see. Okay, so I see that angle EDA, right here, that's a central angle, isn't it? That intercepts the entirety of arc EA. Okay, so if arc EA has a measure of 140 degrees, then that means that the central angle of angle EDA is also 140 degrees. So I'm going to write that down. Angle EDA is equal to 140 degrees. Now, if that's equal to 140 degrees, and I know that those two triangles that are part of that angle are congruent, that must mean that, and I'm going to switch colors again real quick, this angle right here is congruent to this angle, which means that they make up half of the entire angle of EDA. So that means that angle FDA, ooh, and I should put measures too. So the measure of angle FDA is equal to the measure of angle FDE, which is equal to 70 degrees because it's exactly half of that, right? So now I can, by a little bit of subtraction in the triangle sum theorem, I know that this is 20 down here, this is 70, which is 90, meaning that this must be a right angle and that must be a right angle. So now that we have that determined, we can now use some trig to find the other two sides of that smaller triangle. So let's go ahead and do that. I'm going to use this angle right here, and I have the hypotenuse, and I need the adjacent side and the opposite side. So I'm going to call this N, and I'm going to call this side M for now. Okay, just for simplicity. So I have the cosine of 20 is equal to the adjacent side N over the hypotenuse, which when I simplify that, I get N is equal to 5 times the cosine of 20. Okay, and then I'm going to do the same thing with sine of 20 degrees is equal to M, the opposite side over the hypotenuse. Simplify that, and I get M is equal to 5 times sine of 20. And I'm going to plug those into my calculator. So 20 cosine times 5, that equals 4.7. Okay, so 4.7 centimeters. And then right here, M sine of 20. So let's do 20 sine times 5. And that equals 1.7 centimeters. So 1.7 centimeters. There we go. So that gives me both segments EF, FA, and FD. So all three of those segments. All right. So we're good there now, there. So let's see. We're nearly finished. We're getting close. Now we just need to look at this big triangle over to the left side with those tangents intercepting point G. So now we need to just figure out these angles and side lengths to the left. So we really just need at this point GF, GA, GE, and then the measures of angles GEF, GAF, and EGF and EGA and AGF. So just a couple things left. We're making great headway. So let's look at, okay, the measure of angle AGE. Well, how can we find that? Well, we do know that the form of this figure on this left side is actually a kite, right? Because the two sides on the right, both sides ED and AD, those are the same. And we know that two tangent lines from a point off the circle, those are also congruent, okay? So we have a kite, which is a quadrilateral. So we have segment, or if we're looking at it, this is the quadrilateral I want us to look at. GEDA, okay? That's the kite. Now, we know angle EDA to be 140 degrees, okay? So we've got 140. I'm just going to write this over here. And then we know that tangent lines meet radii at a right angle. So GAD and GED are both right angles right there, okay? Which is another 180 degrees that we've accounted for. Okay, so when we add those up, we get 320 degrees. And then we think about, okay, well, how many degrees are there in a quadrilateral? Well, there are 360. So I can figure out how many degrees angle AGE is by taking 360 minus 320. That will be 40 degrees. So the measure of angle AGE is equal to 40 degrees. Okay? Now, if segments GE and GA are congruent, that makes this an isosceles triangle, right? With EF, or excuse me, point F being the midpoint between EF and FA, excuse me, between E and A, which means that this angle up here is bisected. So I can find each of those smaller angles by just dividing it in half. So let me go down here. The measure of angle EGF is equal to the measure of angle AGF, which is equal to half the measure of angle AGE, which is 20 degrees each. Okay, so we have 20 and 20. That's awesome. So now we're to our last stages. We just need a couple more line segments, their lengths. So now I can use trig, okay? I should also find GAF and FEG. I should also find angles GAF and GEF, which I know that this is a right angle, so I'm going to just subtract 20 from 90, and those are each going to be 70 degrees, okay? So I can say the measure of angle GAF is equal to the measure of angle GEF, which is equal to 70 degrees. Awesome. Now let's use some trig to find GE and GA, which I know that they're going to be the same length, right? And currently, I know the side length FA, right? It's up here somewhere, I know it. I named it N, so we're looking right here. And let me switch pen colors one more time. I'm going to go back to red, I think. So N, so it's actually 4.7 centimeters. So I'm going to use some trig to find both the hypotenuse right here and this leg there. So first I'm going to find the leg, actually. So I'll do tangent because it's opposite over adjacent. So tangent of 20 is equal to the opposite side, 4.7, divided by the adjacent side, which I'm just going to call, let's see, I'll call it alpha. We're running out of variables here, so I'll call it alpha. All right, so then I'm going to do some algebra. I'm going to multiply both sides by alpha and divide both sides by the tangent of 20. So that cancels off, those cancel off. Oh, tangent of 20. So now alpha is equal to 4.7 divided by the tangent of 20. Okay, so I'll take care of that in just a minute and see what that equals. But the next thing I want to do is look at this one right here, which will be, oh, that's alpha. Whoops. I should label alpha. And then I'm going to look at this one, which I'll call beta and beta, because I know that GE and GA are the same. So this time I'm going to use the opposite side and the hypotenuse. So that is sine, so SOH, right? So the sine of 20 degrees is equal to the opposite side over the hypotenuse, which is, in this case, beta. Then I'm going to do the same thing where I kind of cross multiply these, or multiply and divide, and I get beta is equal to 4.7 divided by the sine of 20 degrees. All right, let's plug that into my calculator here. So the sine of 20 degrees times 4.7, that is equal to 1.6. That doesn't look right. Oh, that's because I did it wrong. 4.7, zoops. Shoot, 4.7 divided by the sine of 20. There we go. That's what I needed. That looks a little bit more correct. So 13.7 centimeters. And then 4.7 divided by the tangent of 20. 4.7 divided by tangent of 20. And that is 12.9. That looks much better. So 12.9. So this is equal to alpha, which is our GF. And this is equal to both GA and GE. All right. Whew. We have made it. We have all of our angles, all of our side lengths. We've got it all situated now, okay? So let's try this second one on the second page. All right, the second page and number 2, all the way to number 2. So here they have given us very minimal information, okay? They say the diagram below ABC is equilateral and all circles are tangent to each other and the sides of the equilateral triangle. The radius of the 3 smaller circles, circle P, Q, and R, is 4 centimeters and the radius of O is not given. We need to find the radius of O and the lengths of the side of the the equilateral triangle. Okay, so they have not given us an immense amount of information, so we need to do a lot here to extrapolate. So one thing that we know, first of all, is that if we were to write in the medians and altitudes and everything, they actually are all the same line on an equilateral triangle, okay? So, whoops, it's a little off. Let's try that again. That should be closer. There we go. So that, and if we were to draw one from any of the vertices to the opposite side, which I'm going to rename those angles as well, or I'm going to name those points as well really quickly. So this will be N on the bottom, M, and L, just so we have some more reference. So if I were to draw a segment BL, or AM, or CN, those are all going to cut this triangle directly in half, which gives us some interesting information because we know, and they'll all be perpendicular as well, sorry. So this is perpendicular, it's a right angle. We also know that the sides, or the angles of an equilateral triangle are all congruent at 60 degrees, okay? Which means if we cut one in half, each half will be 30 degrees, okay? So we have what we call a special right triangle here, a 30, 60, 90, where one angle is 30, one angle is 60, and one angle is 90 degrees, which means that we can also use trigonometry on this angle, or on this triangle as well. So that is of great benefit for us. Now, we need to go from the fact that just one radii is 4 centimeters, okay? So we need to figure out how to get from that to the radii of that larger circle, and then being able to use that to calculate the side length of one of the sides as well. So the way that we're actually going to do that is we are going to go ahead and draw another line. This will be a radius to segment CB, right? It's a radius, and we also know that CB is tangent to circle O, which means that the radius that touches that tangent point of tangency, that's going to be a right angle, okay? Now, I'm also going to draw another line in here from vertex B to to the center of circle O, all right? So now you might even be able to see some more right triangles, okay? So if we look just at the right side of this, we have a right triangle here, here, and here, okay? Now, interestingly enough, these right triangles are actually all congruent, okay? Now, let me explain that a little bit, all right? So I'll erase some of these phantom lines and some of those arrows. So let's look at first triangle COM and BOM, okay? So COM, we're going to prove that they're congruent, okay? We know that CB is bisected by point M, okay? Because if we were to extend this line from A all the way to point M, that would be an altitude, that actually bisects an equilateral triangle, okay? Just like CN did for AB. So we know that CM is congruent to BC, or excuse me, congruent to BM, okay? Then we also know that the point of a vertex to the center of a circle is going to be the same for every equilateral triangle. So, or for every point of the center to every vertex in an equilateral triangle. So that means that CO is congruent to BO, all right? And then lastly, we know that OM is congruent to itself because of the reflexive property of equality, okay? So now that we've got that taken care of, that's great, but we need to look at BON now. How about that? How does that compare? Well, I know that if M is the midpoint of CB, and N is the midpoint of AB, that means that if those two sides, AB and CB, are congruent, then their halves must also be congruent. So BN is congruent to BM and to CM, okay? Then the last thing is, well, I saw that OM was congruent to itself, but OM is a radius of circle O. Guess what else is a radius of circle O? ON, okay? So that means that that is congruent there as well. So we've got some interesting facts about these triangles, right? Where this is 30, this is 30, this angle up here is 30, and then this is 60 degrees, 60 degrees, and 60 degrees. So we have three congruent triangles, okay? Which is really, really interesting for us. Because of that information, we actually know something special about a 30, 60, 90 right triangle as well, okay? So we know that the shorter leg, and I'm going to draw this out here just for a little bit of clarity. Oof, let's try that again. I'm going to draw this out here for a little bit more clarity, where let's say that this is 30, this is 60, and then this is our right triangle, okay? So what I'm going to do is I'm actually going to name this side right here 1. And then I'm going to do some trig on this, okay? So to find the other three, or the other two side lengths, okay? Just so that we can get a reference for what we're doing here. So if I were to want the hypotenuse, I'm going to use 60 as my reference angle, and I'm going to say, well, I have my adjacent side and I want the hypotenuse, okay? So let's call it H instead of a 0 or a circle. So I'm going to say the adjacent side is cosine, the adjacent side over the hypotenuse is cosine of 60 degrees equals the adjacent side over the hypotenuse. I need to do some rearranging there, just like we were doing on the last page. So I will get H is equal to 1 divided by cosine of 60. Now, I'm going to go ahead and plug that into my calculator. Oops, here it is. So I have 1 divided by 60 cosine. Interesting, I get 2. Okay? So that means that my hypotenuse is actually equal to 2 if this right here is 1. So this is actually true in every 30, 60, 90 right triangle. The shorter leg is exactly half the length of the hypotenuse. And the hypotenuse then is exactly twice the length of the shorter leg. All right, so I'm going to say, well, if OM, I'm not even going to name it right now, but I'm going to say that twice the length of OM is actually going to be equal to, let's see, segment CO, okay? Because now let me use a different color here to kind of highlight this. Right here, that's the hypotenuse of this 30, 60, right, 90 right triangle, and this is the shorter leg. So I know that the hypotenuse, based off of this little proof up here, I know that the hypotenuse is exactly 2 times the length of the shorter leg, okay? Now, we're going to do something else with that that's pretty interesting in a minute as well, because I know that this is the same length as OM, right? So ON and OM are congruent, which means this is, if we want to use it, it's like a 1, but I'm putting that in air quotes, okay? And then this up here, CO, that would be, if this is 1, that would be 2, Okay, so if we're looking at it, CO is actually 2/3 the length of CN, that entire altitude there, okay? Which will be interesting for us in a moment. Guess what else? This point right here, that's going to also be 1 because it's another radius. So really, we have this thing separated out into 3 segments, okay? If we want to segment this a little bit, this is 1 because there's the radius. Here's another, and then the third part is from O to N. Okay, so we have that separated into 3 parts, which is going to be very interesting for us in just a minute, okay? But the next thing that we need to do is we need to say, okay, how does this all relate to our radius? Well, we can see that point R, and I'm going to use point R here, that actually is on the exact same line, this altitude line, as point O. Okay, so what that means is that, well, we can dilate and translate point R to coincide with point O. Okay, and if we do that, it's actually a dilation where the center is at point C. And guess what? From this point right here, that line that we drew in, down to N, that is a multiplication of 3, because if this is our 1, which it's not actually 1, right? We know that the radius of circle R is 4, so we're just using an arbitrary one. Then going all the way is 1, 2, 3 jumps, okay? So we know that actually circle R is exactly 1/3 the size of circle O, which means if we multiply circle R's radius by 3, we'll get the radius of circle O. Okay, and what is 3 times 4? Well, that's 12 centimeters, okay? So we were able to actually find the radius of circle O based off of that fact of separating this out and kind of segmenting the entire altitude out into those 3 parts based off of what we found with those similar right triangles and those congruent right triangles, right? So now we have gotten the radius of circle O. Now we just need to find, okay, what is the measure of the side lengths? Well, I have a shorter leg here, and I have an adjacent leg, or a longer leg there, and I know this angle measures, so I'm going to use trig. I have the adjacent side and the opposite side, so I will say that tangent of 60 is equal to the opposite side, which we don't know. I'm going to call it y, the opposite side over the adjacent side, which is 12, okay? So then I will multiply over, so I get 12 times the tangent of 60 is equal to y. All right, so let's go ahead and plug that into our calculator. 12 times 60 tangent equals, that is 20.8 centimeters. So 20.8 centimeters is equal to y. Now that is only segment CM here, okay? And they asked for the entire side length of this equilateral triangle, right? So if we know that CM is half of the length of CB, we're just going to multiply it by 2. So segment CB is equal to 41.6 centimeters. And there you have it. We have gotten now the radius of circle O and the side length of your equilateral triangle. There you go.